themselves, and they just form this formation, my three spin. They're all running a separate one. Max is the disturbance. He's pushing one, you see the others track. The communication we actually simulated in a simulant model for this, but it's running three separate estimators, three separate controllers with limited information between the cart. Now the interesting thing about no cart has an observable set of measurements in the system. Each is just getting one measurement. It can't see the whole system, but you can still set up this problem and get a solution for this. Even though no one cart can observe everything, the combination of all of them is observable, of all the measurements. So we did it also for a digital one, but here's the communication link states. So cart 2 talking to 1, that means it gets through. These are the dropped packets in those links. So you see the rough ratio of dropped packets. And here's the performance. Now, the thing I should point out about here is the two different time scales. Here's the cart positions. You see them forming, going into formation, and this is a time scale in the 20 seconds across here. Here are the estimators. We're 0.01 of a second here. The estimators in this system are running 100 times faster than the control algorithm, because those carts are really not high-performance devices. But you can build a high-performance estimator on them. So you see what happens in the estimation. For each estimator here, the distance between 1 and 2, 3 carts are estimating that same variable. The cart that actually gets to measure it is the blue one, and it has just an exponential decay. The other carts get some of their information through the communication links and through the observation of the movement of the carts. So they don't have an exponential there. You see a bit more of a transient. But within about 0.05 of a second, they've nailed the error. So the estimators are performing excellently. You'd need to have much, much more expensive carts in order to get the control to make use of that information. But that's really just to show you that we did actually manage here to design controllers for this particular system. Okay, here's my conclusion here. I think I've said almost everything here, so I'm not going to spend any time on this. That you can get a distributed estimator outperforming centralized solutions. That if you run things in parallel, you will get disagreement, and consensus requires you to have communication, and has a requirement on having a spanning tree. Information has to be able to flow from one point and eventually reach all the other points. That's even true if everybody gets to measure everything that's going on. It's still the case. The minimum number of links, and this is interesting, only grows linearly to gain control of this. And you have to listen. Listeners are much more important in the cooperative network than transmitters. And the last one was we basically do have tools for doing these design methods for them. So at that point, I want us to keep you late and take any additional questions.
Questions?
Yeah.
What are some of the advancements to these approaches when you want to apply in the multi-robot coordination and exploring unknown environments?
Well, here I've sit down and gone to the basic rules where the environment is well modeled.
Right.
So, all I have been exploring the issues that come around from essentially errors that arise from not knowing exactly what your cooperative agents are doing. Now, when the environment is also unmodeled, there's another element of error that grows into the system there. And so I haven't begun to address that particular aspect. It is only going to get worse, as you might imagine. Here I'm just attempting to clarify what happens even in a perfect environment, to at least establish a baseline on that.
You started with this issue of this 10 to minus 13.
Oh, yeah.
So then, as a conclusion, what would you say? Is no problem?
Well, I wouldn't say it's no problem, but let's say, okay, so I didn't tell you the details of how that's done. So basically, the spacecraft do reflect laser beams off each other, and they're in a phase-lock loop, which allows them to detect changes in relative positions, again, of the order of 5 nanometers. So they can get that relative ranging information accurately enough. The difficulty is within the actuation. So you have these tiny little actuators that are, 10th of a Newton or something, and even on a 500 kilogram spacecraft, that would just blow it out of the water in this scale of things. So what happens is you have a hierarchy of 4 actuation levels. At the bottom is the spacecraft thrusters, and they have to position the spacecraft roughly to about a centimetre, to millimetre to centimetre range. Then they're switched off, and the thing is held frozen. Well, not completely frozen, but those are switched off, and then there is an optical table inside with a worm drive that drives a little cart backwards and forwards. And so the little cart then moves into control, and that's position accuracy comes down to maybe about 10 to the minus 5 meters. Then that's switched off, and then there's a voice coil actuator mounted on each one, and that goes down to about micron to 100 nanometers, so 10 to the minus 6, 10 to the minus 6 in that position. Then they switch that off, and then there's a piezoelectric surface on the top of this voice coil actuator, and that turns on, and that gets down to the final 5 to 10 nanometers. So that's basically how. Now, we've managed to use these systems to actually create an interference pattern in a lab with different optical benches, providing the light sources and the combiner on a bench. You have to hold the pattern for about 30 seconds while a mirror scans it across a detector and basically looks for the sync function that gives you the interference pattern, and then tries to find out where the peak of that sync function is. So that part has been demonstrated in the lab remarkably.
What resolution can you get on the planet surface?
Actually, that really depends on the spacing of the spacecraft.
Kilometer thing.
Yeah. So essentially, that's the inverse of that. There's a factor in there, and I don't know what the factor is. But it's thought for detecting and observing these planets that the 2 to 10 kilometer range would give you a reasonable photograph. But it's not. It's really only going to be some. I think you're only talking hundreds of pixels per planet. You're not talking a fine picture. Just a basic color. There's a couple of other things you can do. You can set up this array as almost as a phased array, and this is not quite as doesn't require quite as much precision. And you can create, if you have more than one reflector in there, you can create optical nulls in there. So one of the ideas is to essentially create an antenna pattern which puts the maximum sensitivity on the planet and the null on the adjacent star, and then don't use that to resolve an image of the planet, but instead use that as a selection for the photons and do spectroscopy on the photons and see, get the emission spectra, and so you can determine things like the atmosphere of the planet. So that's probably a more likely one than actual imaging. You don't require quite the level of resolution, but you have to be able to create a phased array in exactly the same fashion by having the individual elements free-flying.
No further question. Let's take this.